I hope everybody is fine. And in this video, I'll be talking about the energy levels of particle in a box, and then the energy levels of electron that's bound to the nucleus. And here we'll have a special reference to hydrogen atom using quasi-classical approach. So so I would like to solve the two problems using quasi-classical approach. The first one is the energy level of particle in a box, in a one-dimensional box, and and certainly what we have is we have a particle in a box whose walls are rigid, and this is my position x equal to 0, this is my position x is equal to L. And one thing should be borne in mind, that we are not considering the spin of the particle. So the particle that we have in this one-dimensional box is a spinless particle in one-dimensional box. So my x is 0 at one rigid wall, and the length of this box in one dimension is equal to L. And we can see that the potential has two rigid walls. One is at x is equal to 0, and another is at x equals L. Now, in order to find the energy levels, what we do is we make use of the quantization rule that we have already obtained for using the quasi-classical approach, using this WKB approximation. Now, in this case, the momentum of the particle will be constant between 0 to L. So since the momentum is constant, then the P of x that we have, that is under root of 2m e minus v of x, and this v of x is immediately equal to 0, so this p is under root of 2me. And we can easily inculcate the quasi-classical approach to calculate the energy expression for the particle within this well. And the integral that we have already obtained is quite simple to calculate in this case. And what will be the integral? The integral will be simply integral 0 to L p of x, then d of x is, for p of x we will have, this is from 0 to L, we will have under root of 2me, and then we will have d of x. And we understand that this integral is, if n is extremely large, this is simply n pi h bar, and we can have this under root of 2me out. So inside we will have integral 0 to L, then we will be left with simply dx. So this dx will be n pi h bar. So we will have this x as L, and so this is L times under root of 2me is equal to n pi h bar. So here we can immediately think of En, because we have an integral number n. So on squaring this equation, we will have L square is times 2m En equals n square pi square h bar square. So from here we can calculate the energy, and the energy is n square pi square h bar square by 2ml square. So this is exactly the energy of the particle in a one-dimensional box, and this is the exact expression for the values of the energy of the particle in this infinite well. So this is the outset of one problem. Now let's go with another one, where we have what we have is, we want to calculate the energy levels for an electron which is living in the domain of this nucleus, of whose charge is ZE. So since we will take down this approach to the hydrogen atom, so for that Z will be equal to 0. So we have electron living here within the potential of this nucleus. And what we will do here is we will use the quasi-classical approximation to calculate the energy levels of the state of the electron that is bound to this nucleus. Now, what is important here is that this electron is moving in the Coulomb field. And that Coulomb field we can think of as V of R is equal to minus K E square by R. So what am I doing here? I'm using Z equal to 1 because I want to boil down it to the hydrogen atom. So this K, we know this K is 1 by 4 pi epsilon naught. So this is our K. So this is our Coulomb potential minus Ke square by R. Now, since this electron that we have, this electron is bound to the nucleus, and it can be assumed to be moving between the two rigid walls. We can assume this electron to be moving between two rigid walls from 0 and R and A. And E, if we think of E at the edge, this E at the edge, at the boundary, this E is nothing but V of A. All right, and this A, we can think of this A as the separation, the maximum separation from nucleus to the point where to the region where electron is actually orbiting. Electron is feeling the potential of this nucleus. Now, what is important here is that the energy of this electron is negative because this electron is bound to the nucleus. Now, so if I think of using the quasi-classical approach here, what I will have is I have a situation like this. I have a situation like 0 to A, then under root of twice M, then E. Minus will become plus. So this is plus K E squared by R dr. And for large quantum numbers, this is N is pi, N pi H bar. So I have to solve this integral to calculate the energy states, to calculate the energy levels of the states of an electron that is bound to this nucleus. And I will have to use the value of a standard integral here, which can be calculated using residue theorem. And what is that? That is integral 0 to A, and then if I have 1 minus A by x of dx, this integral is simply pi A by 2. All right, so we have to keep this thing in our mind that we'll be using the value of this integral while solving this problem. So we can see here that if I write down, if I take this under root of this is under root of so integral from 0 to A, and if I take under root of minus 2m E out, and because I want this integral to be boiled down to a situation like this where I can directly use the value of this integral. And for that, okay, if I take under root of minus 2m E out, then here I'll be left with 1, and then here I'll be left with minus, and here I will have K E square by R E. Okay, this will be the case. dr is n pi h bar. Okay, so now from here, let us see where we'll reach out. Now, I would like to write it again. So I have under root of minus 2me times integral 0 to a, then 1 minus ke squared by re, then dr is equal to n pi h bar. Now let me use this minus ke squared by re equal to a by x. Let me translate down this integral into x. So this is minus ke squared x is equal to a e and r. And if I take its derivative, I'll have minus ke squared dx is equal to a e dr. So from here, we can write down the value for dx. So what is dx? Dx, no, I want for dr. So dr will be minus ke squared dx by ae. So I can so here it must be r in general because and this when we'll be using it for, so this is dr, this is dx, and we can see here, you can check it here that we will have for x is equal to for r is equal to 0, we will have x equal to 0, and for r equal to a, we will have x equal to a. It can be easily evaluated down here. So so we can use these approximations in the above equation. So what we will obtain is, okay, what will come out, I think minus ke squared by ae will come out, okay, for dx. And then we have integral 0 to a, okay, then we have I have forgot under root of minus 2me. All right, and then we will have so this is 1 minus this is if I take that out, so this will be, so here we will have minus this minus ke squared by re is a by x. So so I can think of one how do I have minus here? It has to be plus first, okay? So here, okay, if it goes inside, then this will be, so this is under root of minus 2me. When it goes inside, you will have 2me, that 2 minus, but here we have plus, and if this is plus, so it has to be minus, and this is also plus, so this also has to be minus, okay? So minus ke squared by re is a by x, so that's the point. So I have committed a mistake over here, so this is minus 1, so here it is minus 1, and 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 what am I going to write now is so this is minus 1, then plus, because I have taken minus ke squared by re out, so this whole thing is a by x. So here I'm going to write down a by x. Dx is equal to n pi h bar. That's the case, right? And we can write down this as under root of minus 2me, then we have minus ke squared by ae, then we have exactly the integral that I wrote down, 0 to a, this is a by x minus 1, dx is equal to n pi h bar, but the value of this integral is pi a by 2, so we can use that that value as, so this is minus 2m e times minus ke square by ae times, so here we will have pi a by 2 is equal to n pi h bar. So I think this a and a will go. Okay, this goes. Now what we can do is we can translate down the things. This is minus 2m e is equal to, so this e will go up. I think the better thing is to do the scaling now, because we want to get rid of this root. So in doing so, what we'll have is, so on scaling I will have minus 2me here, because scalar and root will cancel. Then we will have this minus will turn to plus. So this minus will turn to plus. This will be k square e to the power of 4 by e square. So this will be k square e to the power of 4 by e square is equal to, not equal to, I mean, this will be pi square by 4. So this is times pi square by 4 is equal to n square pi square h bar square. Okay, then we can have this square out. And if there is anything else that we can stop down, no. Now we can think of e, so this e will become en. All right, any cancellations? I think this pi square and pi square will go, and we will have minus here. Okay, so this e is taken here, so what I'm left with is minus 2. 2 is here, m is here, then k square is here, then e to the power of 4 is here, and what else is here? And I don't know, I might have committed some mistake as well, but let me think in terms of the numbers here. So this is divide by, so this is n square h bar square. I think this is all done. Okay, okay, this e has gone here, and this whole thing will remain as minus 2m k square e to the power of 4. Then we will have divide by 4 here. This is 4 n square h cross square. So this is my en, and let me go with it. This is en is minus this 2 and 4 will go, so this is minus m. Okay, then k is, what is k? K is 1 by 4 pi epsilon naught. This is m, then this is e to the power of 4. Okay, then this is 2 times 4 times 4 times epsilon naught square times pi square n square h bar square. So what we have is en is minus m e to the power of, so this is 16 times this is 32. Then we have pi square, then we have epsilon naught square, then we have n square, then we have h bar square. So this is exactly what is the energy, what we call as using this formula we can calculate the energy levels of the S state of an electron, and the S state, the closest state where L is equal to 0 of an electron in hydrogen atom. That's it.